Thank you for that kind introduction. It's always a pleasure to be here at MIT. I have an occasion now, and I won't say about it, to come here more often, and so maybe I will do that. I should do two disclaimers before I start the talk today. The first is, this is ongoing work. I'm hoping we'll have stuff uploaded to archive before the year ends. It's work in control, and I figured if I want to talk about something new in control, I've never presented this work before, LIDS is a perfect place with its eminent history in control theory to do that, so I'm excited to do that. The second disclaimer that I want to do is, I'm going to do a major transgression and not talk about machine learning in this talk. So I'm going to apologize to the machine learning gods, to forgive me for that. So there won't be any machine learning in my talk today. So this is joint work with two of my current PhD students, Judy and Reza. We'll get into the details in a moment, but it's something I've been thinking about for quite some time in terms of how we could, or how is it possible perhaps to extend some techniques that are very classical in control theory to maybe a wider range of applications. And so let me get into that. So here's the outline. I'll briefly say a few words about, convexity and control, in particular non-quadratic convex costs and issues that come up in control when one wants to study to go beyond quadratics. I'll introduce something called Bregman divergence. Many of you may have heard about it, but maybe I'll present it from a slightly different perspective. I want to apply Bregman divergence to control. That's most of the talk. I'll give some examples of the utility of this, and then I will conclude. If you've been in signal processing or machine learning or statistics, you all know that in the last 3 decades, there's been a lot of work moving from, quadratics and least squares and least mean squares, this kind of things, to convex costs that are not quadratic. So when I was in grad school, SVDs and subspace methods and so on were all the rage. Everything was kind of quadratic, but you've all heard of L1, lasso, compressed sensing, things like this, low rank matrix recovery, nuclear norms. In machine learning, then I am not transgressing maybe. People use cross entropy loss a lot. Out of MIT came this notion of atomic norm minimization. So it's had a big impact, and it allows people, when they're looking for solutions, to impose structure or to recover models that are, or behaviors that are not easy to recover if all you're focused on is just quadratic loss. But in control, I would like to argue that people have not been able to do that to the same extent. Largely, if you look especially at classical control, people focus on quadratic costs. So there's the famous, LQR, LQG criteria where you have a quadratic cost on the state of your system. In this talk, X will always be the state. A quadratic cost perhaps on your control. U in this talk will always be the control signal. And so some expected, quadratic cost of those. Even in H infinity, people still, they look at energy gains or quadratic costs. You have disturbances, you measure as energy, and again, you have your cost up here. So things are typically quadratic. And so the question is, why is that? Why haven't we been able to look at other things? And so let me begin to slowly go into this. So I'm going to take a very simple example to begin with. So this is just a linear time invariant state space model. That's what I'll stick throughout this talk. X is the state, U is the control. It's an n-dimensional state. In this case, it's a scalar control signal. There's some initial state, which we assume we know. And so the classical linear quadratic regulator problem just attempts to minimize. You have 2 quadratic costs defined through 2 PSD matrices R and Q, quadratic on the state, quadratic on the control, and you want to minimize this over this sequence of control. So this is clearly just a quadratic problem. There's only one unknown in it, which is the initial state. So you can certainly do that. That's the LQR problem. Now, if I want to look at this thing more generally, well, clearly what I could do, I can take two general convex costs. I'll use Q for the state cost, R for the control cost. Just replace these quadratics by this. And so this is clearly, again, a quadratic cost subject to a bunch of linear constraints. Again, the only unknown is x naught. So this is not a big deal. You can solve this. So just to spell it out a little bit, I'll take a very special case. This is the LQR problem. So I want to minimize the quadratic cost subject to the state space equations. And here, all I'm doing is I'm going to replace this quadratic cost here with an L1. So an L1 penalty on the state. And so those of you who know L1 pushes things to sparsity. So when I do this, I'll get sparsity both in space across the state vectors, but also across time, because you add the L1s, it's essentially the L1 norm of an aggregated vector. So I expect that this will give me somewhat sparse solutions. And so these are both convex optimization problems. I can solve them. And here is what you get if you just solve what I wrote there. This is for some fifth order system. The system doesn't matter. The blue curve is, so I'm here writing the magnitude, the 2 norm, if you will, of the state. The blue curve is what you get from LQR. It's a linear controller. You know, when you have linear systems, everything decays exponentially. That's what happens. The L1 controller, the one that has the L1 on the state, at the beginning doesn't do as well, but it pushes the state absolutely to 0 after 25 steps. It wants something that's sparse. It will do that. In fact, you know, if I put a weight in front of this matrix, or excuse me, in front of this L1 norm, and crank it up, this happens earlier and earlier. And if you crank it up sufficiently, at some point it will set the state to 0 after 5 steps, which, because the system I was looking at was controllable, is the shortest amount of time required to push the state to 0. So the point I want to make is that, you know, this is not just, you know, for curiosity. You can get behaviors that are very different from what you get from LQR by just changing that cost to an L1. This is now something that is going to push the state to 0 earlier. Yes?
Sorry, what's the control doing when that state is being driven more rapidly?
I will show you later when I add noise. I will show you that in much more detail. This is all motivation, but that's an excellent question. It will be doing more, of course, but I will show you all of that. Thank you. Okay, so, you know, you can do other crazy things, and so I'll maybe go over this quickly. I can put, for example, a peak bound on the control. You know, so I can say if my control is within an interval of, you know, delta, I will penalize it quadratically. But if you exceed this, you're not allowed to exceed this. I'm going to give infinite penalty to that. Again, this is convex. I can put my L1 norm here. I can add that. I can solve this. It's a convex optimization. And then here's an answer to your question. So here, again, I have the magnitude of the state. This is a second order system. Here, the red is the LQR. The blue is what this controller does. Again, it pushed it absolutely to 0 after 5. But because I had a constraint on the magnitude of the control, at the beginning, because the LQR applied a pretty large control, this one couldn't. The performance got a bit worse before it, you know, got in better. And here, it's exactly your question. You can see what the LQR controller did and what this controller did. And so once you hit 0, it doesn't have to do anything after that. So you can do, in principle, you know, so why am I even giving this talk? I just showed you can put, you know, convex costs, and you can get behaviors that are qualitatively different than what you get with an LQR controller. And there may be reasons why you want to do this. I might have a control system where, in fact, I do have a peak constraint on the control. So these make sense from a practical point of view, certainly. So what is the issue? Why am I giving a talk? So there's, you know, as I said, you can get these exotic controllers if you want through convex optimization. But there's at least 2 issues. The first is, you know, for a fixed horizon, if I want to solve these problems as a convex optimization, There's quite a bit of complexity. The complexity grows polynomially in the horizon t, typically like t cubed. So that could be problematic. The LQR solution, because it has dynamic programming built into it, is actually the complexity grows linearly with the horizon, not cubically, so it's much better. But in particular, we cannot solve infinite horizon problems this way. And if you want to, there's no stability guarantees with this. So people do like, you know, I don't know what they call them, but they do these things in blocks and stitch them together and hope that everything works, and who knows if it does. But the bigger issue is that, you know, any respectable system has noise in it. Okay? So there's a noise. There's something also, you know, disturbing the system that you're not fully aware of. And typically, you know, people say this is maybe zero mean and IID, and that's what I will assume. And so this precludes us from doing a simple deterministic optimization, because in the previous case, the only unknown was the initial state. Here, there's this process constantly hitting me, which is unknown. And so the way you have to deal with that, of course, is you can no longer talk of the cost, but you now have to talk of expected cost over, you know, the randomness and the disturbances. You also need to be very careful about what information is available to the controller. In the previous case, the unknown was x naught, so all the control signals at different times could be a function of x naught. It was not a problem. Once you're in this setting with noise, it really depends on what the controller knows. And for the majority of this talk, to make things simple, I'll say a few words about more general cases at the end. I'm going to assume something that's called a full information controller, which means that the control signal at time I gets to see the state of the system. It doesn't see the disturbance, but it sees the state of the system. So its control is allowed to be a function of all the states it's seen, which are all the states xj up to the current time. Okay, so that is the information available. And so when you think of this kind of setting, the optimal control is not really a signal, it's really a policy. So it's really, you know, based on my observations, how do I, you know, it's really these collections of functions f that determine the control. So I'm looking for a policy now, okay? And so if I just want to write it up, this is the optimization problem that we want to solve. We still have the constraints. There's noise here now. And I'm looking at minimizing over this policy the expected value of, say, this convex cost. Okay? So that's what we like to do. And now I want to convince you that even though this looks very easy, it's easy to write, it's actually very difficult to solve. And so to do this, I can show the difficulty in just a very simple toy example. So let me assume the system is scalar. X is a scalar. Control is a scalar. The noise is a scalar. Let's assume it's Gaussian, standard normal. I'm going to assume the cost on the control is simple quadratic. And I'm going to assume the cost on the state is the absolute value. So it's the one norm for a scalar. And you'll see already this will become complicated. Now, when you're looking at this problem, this is over a horizon t. The way we solve this is dynamic programming. You note that the last control signal at ut, it only influences the state at t plus 1. And so in order to find the last policy, I just need to look at the last terms in this, in that sum. And so this is how you find ut. So I need to take the expectation. That's the absolute value term. This is the quadratic on the control. And so in this expectation, because I'm sitting at time t, the controller knows x. It's going to decide on what u is. So the only randomness here is the noise that hits you right now. Okay? So this expectation is over this w, which is a standard normal. Now, if you sweat or you look up some book or something, it turns out, you know, one can find the expectation of the absolute value against the Gaussian. It has an exponential term. It has a Q function. Q is the tail of the Gaussian. This is the formula for it. It ends up being a function of the absolute value of this deterministic part. And here, of course, is that. And so I have to minimize this. This is convex, so I can numerically minimize it if I know what x is, and a and b I know. And so you minimize it. you get your u. Okay, so I can numerically compute this, and I can take this u, and I can plug it in, and I'll call this thing m. This is like the cost to go. So if I'm sitting at time capital T, and I minimize this from the vantage point of the time before me, this is the optimal cost to go. It's sometimes called the value function. And as I said, you can numerically compute it, but I don't know it in closed form. Already, before the minimization, it already had Q functions and whatever in it. And so the challenge is now if I go to the next step, so if I want to find the control at ut minus 1, I have to take this optimal cost to go and add it to my current cost. This is dynamic programming to get this expression here. And I've replaced xt in terms of ut minus 1, the previous state, and so on. And so here I have to do this expectation over wt minus 1. So this part of it I know how to do it as Q functions and everything. This I don't. Because this m function, I don't even know it in closed form. I have to compute it. And so the only way I can do this expectation is through Monte Carlo. So every time I want to find out what it is, either if I want the gradient or the value to somehow optimize this, I have to generate different realizations of W. For each realization, I have to solve the problem on the previous slide to find m and so on. And so this is cumbersome, and you can imagine if I do this 2 or 3 steps, I will have these nested optimizations, and it exponentially blows up in your face. And so nobody does this. At best, you can do this for 2, 3 steps in advance, and sometimes people do. This is sometimes called receding horizon control. So you make a control action looking 2 steps into the future. But this is not something that you can do. Okay, so that's, in a nutshell, why no one does this. Okay? And so you might ask, well, what is going on in the quadratic case that allows us to do everything? And so let me explain that, because we will get cues from that as we move forward. So in the quadratic case, if I look at time t, my costs are both quadratic. The cost on the control and on the state, which I have spelled out, everything is quadratic. And so this expectation is very easy to do, because if I take this quadratic and I expand it out, there's a quadratic term. These are deterministic. This is random and 0 mean. So the deterministic terms come out. There's cross terms involving this random times this deterministic. Those in expectation go to 0 because W is 0 mean. And so you're left with the quadratic term in the random stuff, which has some expectation. Doesn't matter. It's not a function of U. Okay? So the important thing is when things are quadratic, this expectation is trivial, and essentially it amounts to dropping W. This is the term that matters. And so your optimization now is just a simple quadratic optimization. You can take derivatives or complete squares or whatever. You get a control law, which is now linear in the state. And then this, you can plug this back into here or do Schur complements or whatever your favorite method is. The important thing is this cost to go is quadratic. It's a function of A and Q and all the parameters, but there's a center matrix sitting here. It's quadratic. And because that's the case, when I go to the next step, I just have to take this quadratic cost to go, add it to the quadratic, Q here, which is the current cost, and then this is the cost on the state. So everything remains quadratic. I know how to do the expectation here once I replace xt with ut minus 1 and xt minus 1 and wt minus 1. So everything remains quadratic. The expectation keeps quadratic. The minimization keeps things quadratic. And so tracking what happens to this center matrix, this object, is really what this Riccati recursion is, for those of you who know what it is in control. It runs backwards in time. Okay, so things worked out because both the expectation and the deterministic minimization kept everything quadratic. We never got into more complicated and more complicated functions where, after a while, we just have to throw our hands up. Everything was self-contained and easy to do recursion. So I would like to mimic this, if possible. And before I go into how to do that, I will just make one comment that I'm going to focus on infinite horizon problems. So in the infinite horizon case, it's the same control policy, full information, causal. except that the cost will be the following. I will look at a finite horizon cost, divide by 1 over t, take the expected cost, let t run to infinity. This is the object I will try to minimize. And again, I don't know if I should show this. If you attempt to do this, then you get what's called the Hamilton-Jacobi-Bellman equation, which is essentially the following thing. So you're looking for m, which is a value function or cost to go, which has the property that when you take m and you put in ax plus bu plus w in it, so like the current state, this is the cost on the state, this is the cost on the control. I have to average over w, or take expectations over w, minimize over u, and I have to get the same m back. Yes?
It seems to me in continuous time, this would look, I don't know, more, you get more traction.
Yes, I think you will. I haven't looked at it, but you would. But thank you for that. Anyway, so this was just a side remark. What I want to do is really to try to connect to the quadratic thing. And I will just say one thing because it's important. The good thing about this is if it also comes with a guarantee of stability because this m plus q, I'll call it p, is a Lyapunov function that guarantees stability, but I won't go into that. Okay, so what is it that I want to do? So this is all introduction for me to get to this concept of Bregman divergence. Okay? So if there's one thing I want you to take away from this talk is that the closest thing to quadratics is Bregman divergence, and I'll show you why. So if you have things that work for quadratics and you're wondering whether they can extend to anything else, I would always try out Bregman divergence. Okay? So how does this thing work? So you start off with a convex differentiable function. Some people insist that it be strictly convex, and I'll talk about that. So this is called the potential, psi. It has to be differentiable, or even that can be relaxed. May or may not be strictly convex, okay? And so the Bregman divergence, essentially what it is, so it's a function, it has two inputs in it. And so the way you think of it is this is your, say, convex potential, it's some function. So I look at the potential at the first argument, and I subtract from it the best linear approximation to this function at the point w prime, at the second point. Okay, so I'm sitting at w prime, I draw this tangent to this convex function, and then I'm looking at the difference between the potential itself and its first order approximation. Now, since this function is convex, you know, the tangents are always below, so this quantity is always non-negative. So Bregman divergence is an immediate way where, you know, if you give me a convex function, I can give you something that's always non-negative through this. And so this has nice properties. First of all, it's clear. As I said, it's non-negative. If you're strictly convex, it's 0 if and only if the arguments match. So that's why I prefer things that are strictly convex, because I like this property. So that's one thing. Now there's numerous examples of this. So for example, if I take my potential to be squared Euclidean distance, the Bregman divergence is just, you know, the difference or the squared Euclidean distance of the difference between the two arguments. Okay? But you can take anything else you want. If you take negative entropy, which is convex, then you get KL divergence. The Bregman divergence for entropy is KL divergence. But, you know, choose your favorite convex function and so on. So these things are, even though they're non-negative, they're divergence. They're not distances. There's no triangle inequality. So clearly, you know, this is not a distance. It's the square of a distance in this case. So that's why it's a divergence. But why do I care about this? So if you think about what Bregman divergence is you're taking your convex function and you're subtracting the 0th and first order terms. So everything that remains are quadratics and higher. And so that's why it kind of behaves like quadratics. And let me show you some examples. So we all know, hopefully, from high school geometry, the law of cosines. Because you have a triangle. So if I'm interested in the distance between w and w prime, and I have this third point here, you know, this is this squared distance plus that squared distance, or whatever, minus the 2 times the product of that. So there's a cosine. I mean, this is a whatever, cosine law. there is a Bregman divergence counterpart, which is this. So that's the Bregman divergence, that's a Bregman divergence, that's a Bregman divergence. This inner product takes this form. So if you take the square 2 norm, these gradients are just 2 times the weight vector, and you get that back. Okay? So this is that. More importantly for me, there's a completion of squares, similar to what happens for quadratics. So if you have 2 Bregman divergence terms, there's a W here and a W here. With quadratics, when you do completion of squares, what you like to do is to bring these 2 variables together under one quadratic and then have the leftovers. So Bregman divergence, there's a formula similar to that. So you get the Bregman divergence for the sum of these 2. W sits here. But it's the Bregman divergence of some W star, and then you get these 2 extra terms. And W star is found from this equation. It's sometimes called the normal equation. And so it turns out when psi1 plus psi2 is strictly convex, this mapping, defined through the gradient of the potentials, is invertible. And so there's a unique W star. So there's a completion of squares. So this, and I've made use of this, but the thing that I will make use of most is this next property. So again, for quadratics, let's assume V is deterministic, W is random. Okay? And let's say I want to take the expectation of V minus W mod square. We all know the trick. We've seen this. You add and subtract the mean of W. And so when you then expand things out, you get this term, which is deterministic. There's no expectation. The cross terms vanish because you've added and subtracted the means. You get these 0 mean terms. And then the last term is just W minus its expected value. And you have to take, this is random, so it needs some expectation. Okay? But the reason why this is important is because this deterministic quantity got separated out. It's no longer under an expectation. Okay, so if I need to optimize over it later on, it's easy to do. I got rid of it. There is a Bregman divergence counterpart. Okay? So if I'm looking at the expected value of the Bregman divergence between something that's deterministic and something that's random, the first term, there's no expectation in it. It turns out it's just the Bregman divergence between the deterministic term and the thing that you put here, instead of being the expected value of W, you take the expected value of the gradient of the potential evaluated at your random W. So this becomes deterministic after you take the expected value. And then you put it through the inverse map of the gradient. Okay? And then the second term, which is kind of like this, you just take this quantity I described, and you put the Bregman divergence with the random W. So this term has randomness in it, so you throw an expectation up front. So this has no randomness in it. Okay? So this is what, essentially this is what I will use. It's the counterpart of that. Okay. So here's what we're going to do. So this is the problem ideally I would like to solve, right? I have some stochastic control problem with a convex cost on the state, a convex cost on the control. And the problem is I don't know how to do the expectation. So I'm going to say, I'm not going to solve this. I'm going to solve this. Okay? So this second term I'm really being facetious because they're the same thing. So I'm going to assume my potentials are convex. Let's say they're non-negative. They hit their minimum at 0. I'm going to assume they're even, which is totally reasonable in control. There's no reason to differentiate between positive and negative controls or states. So let me assume that. So this thing here is just a Bregman divergence between U and 0 corresponding to R, because R at 0 is 0 and the gradient at 0 is 0. This is just this. But this term I've changed quite a bit. So rather than minimize the convex function at this, I'm going to minimize the Bregman divergence between this and that. And note that this is 0 when, the difference of these, which is the next state is 0. So I am penalizing the next state, but I'm penalizing it in this fashion. I'm putting all the deterministic stuff to the left. I'm putting all the random stuff to the right. And this is really the key. So I've changed the problem on you, and you'll see why. As you can imagine, this expectation now will be easy to do. Whereas the whole difficulty with the one above was the expectation was what you needed to Monte Carlo and all of that. Okay, so let's do that. So again, I'm going to do dynamic programming. I'm going to look at things at time t.
Babak,
Yes?
can you say a few words about how expressive that change?
Okay, so I will say this. So when the noise is small, so you're looking at the, so if you look at the picture that I had earlier, you know, so ideally you would want to say minimize this, you know, potential. And I'm kind of expanding a bit around it. And so when your noise is small, when your second argument is close to the first argument, then this is a good thing. The farther away it is, you get a bit more difference. I don't know if that makes sense to you. So, I mean, not that W prime has to be close to W. The closer W prime is to 0, so if your convex potential had its minimum at 0, at 0, you know, the tangent is just the all 0 thing, and so the Bregman divergence is the potential that you want. As you move away from 0, it departs. So for low noise, this is very close to actually what you want. If the noise term is bigger, it's not, it's something else. But this is something I always tell my students, right? I mean, we're engineers, right? So we're not mathematicians. So this is a problem you want to solve. This is where the math is. If I'm really smart, I move the math this much. And so the problem I bring you. So that's what I have done. Okay, so this is the problem I'm going to solve. Instead of looking at this, I'm going to insist, this is what I want to solve. The Bregman divergence between the deterministic part and the random part for the potential. So this is what I mean by Bregman divergence control, solving this problem. And I'm going to show you what this means, hopefully, if there's time. So I think I have to rush a little bit. But the point is, if I now do the dynamic programming, if I look at time capital T, I need to do the expectation. So I'll just use the formula. So this was deterministic. The only thing I have to do is here I have to write the expected value of the potential of Q at minus WT and then invert it. Now the point is, if W is Gaussian, or if it has any even PDF, Q is even, the gradient is odd, so the expectation of any odd function against an even PDF is 0. So this is 0. And again, because Q is even, the inverse gradient at 0 will also map to 0. So this whole thing becomes 0. And I had to put the same thing here against minus WT, so I just put 0. And again, I don't even care about this term because it has no U in it. And so lo and behold, when I put 0 here, the Bregman divergence between a quantity and 0, as I showed from the figure, is just the convex function that we wanted. And so my deterministic optimization is this. So it's just like the quadratic case. What happens is you just drop that term, which is what happened in the quadratic case as well.
But as an engineer, you could have made that step directly.
Yeah, but then I would not have any optimality. I would not be able to say what on earth it is that I'm doing. At least I can tell you what it is I'm doing. And there's a second step, which as you will see, is even more critical. Okay? I totally appreciate your comment. Okay, so in principle, I can do this optimization now. It's deterministic. Maybe I can't do it in closed form. I don't know, but I'll call this thing M. And so now I want to do the next step. And so I have to take this guy, bring him here, write xt in terms of ut minus 1, bring in the next cost. I have to do expectation, and I have to do minimization. So I know how to do the expectation with this. That was the whole point of Bregman divergence, to put it here. But I'm back to square one. What do I do with that? Yes? I'm sorry. And so in order to do the expectation, I need this thing to be a Bregman divergence between the deterministic part and the random part. That's the only way I can do the expectation. Okay? And there's only one way that this can be a Bregman divergence. Can anyone tell me or guess what that is? So if I want the sum of the two things, or the difference of two things, to be the Bregman divergence of those two things, There's only one way to do it, and that's when the thing is quadratic. So if I want the Bregman divergence between W and W prime to be a function of W minus W prime, the only way that can happen is if the function is quadratic, which means that I am going to insist that the cost to go is quadratic. Because if it's not, again, I'm stuck. Okay, so I made two things. I changed the problem to Bregman divergence, and I insisted that the cost to go be quadratic, because otherwise I'm stuck. Okay? So you might think I've sacrificed a lot. I hope I convince you that I haven't. Okay, so once you do that, the cost to go is quadratic. This is the equation. And I tried to number it, and I don't know why LaTeX put a 0 in front of my number, but this is the most important equation in this talk. This is the counterpart of the Riccati equation. So I'll speak to this equation quite a bit. And again, this quantity m plus q is the Lyapunov function. So if you can solve this, stability is guaranteed. Okay, so I will say any triple, so any m that's PSD, in fact, I'll make it positive definite in a moment, and any convex q and r that satisfy this equation, if I can find a triple m, q, r that satisfy this equation, I can construct an optimal stochastic Bregman divergence control.
Sorry, no,
yes.
Just to
Yes.
clarify, so you say, so the equation 0.1
Yes.
is a constraint on Q, R, and
And m, yes. So as you will see, I will not be able to willy-nilly choose q and r.
of course.
Okay? What I will be able to do is, as I'll show you many examples, I can choose one of them. So let's say I want a peak constraint on the control. I can choose that. I have a degree of freedom which is m, because it's not as meaningful to me. And then based on that, I can see what q's satisfy this equation. And then I'll look at them and I'll say, okay, this is a reasonable q. Or I might choose a q for some reason and do this, choose m, and as a function of m, look at what kind of r's I get and decide on it. But I will not be able to choose them simultaneously.
So
Yes?
you're saying there are non-quadratic cubes and
I will show you lots of them. Yes, I will show you lots. Yes, yes, yes. So it gives you a lot more flexibility than what you had earlier. I'll show you many examples, depending on time. Okay, let me say a few. So I can parse out this equation a little bit, so it'll be clear how I solve it. And so to do that, I need to introduce this idea of a Fenchel dual. Many of you might have heard. So if I have a convex function f, its Fenchel dual is defined in this way. You maximize over x transpose lambda minus f, so that you're left with a function of lambda. It's called the Fenchel dual. I can talk lots about it. I'm short on time. I'll only say it has certain properties. The dual is convex. The dual of the dual is itself, so this is actually an involution, so it's appropriate to call it a dual. For us, if this f is even, non-negative with minimum at 0, the same is true for the Fenchel dual. This will also be important for me. The inverse of the gradient of the function f, inverse here I mean viewing the gradient as a mapping. It's a vector, if I view it as a mapping. The inverse is the gradient of the Fenchel dual. And if I look at quadratics, the Fenchel dual of a quadratic is a quadratic where you replace the center matrix with its inverse. So that's all I will need. And so let me now look at this equation. Okay, so I want to minimize over u, and I want to get back a quadratic. And so, you know, if you look at the optimality condition, if I differentiate with respect to u, this is what you get. I don't expect you to remember the equation. You get this. If you differentiate with respect to x, because the equation was an identity over x, you get this. Doesn't matter. I can eliminate this nasty quantity. P, if you recall, I had defined as q plus m. Anyway, you can eliminate it, you get this. So it says the gradient of the cost on the control is this quantity. It's a linear function of x, depends on m. But more importantly, the optimal control You just invert this, but inverting this is just the gradient of the Fenchel dual. Okay? So what this shows is significant because it shows the optimal control law is a nonlinear state feedback law. The control signal is a function of the state. It depends on the, I guess, cost on the control through the gradient of its Fenchel dual. It also depends on Q indirectly through the M that satisfies the equation that had Q in it. But it's a nonlinear state feedback law. Okay. Now, I can say certain other things. So if I go back to this equation, this was the equation we wanted to solve. I'll skip. If I go and I take Fenchel duals from both sides, you will end up with this equation here. So this is very nice. It says the Fenchel dual of this P plus the Fenchel dual of the R has to be a quadratic. And so this is usually, so we usually solve these equations in the dual domain. So if I choose one of these guys, the other one is clear. It's just a quadratic minus the other. That's how we will be solving these things. Okay, so here's the main theorem. Here's your system. If you find convex functions QR and a positive M that satisfy this equation, this is like the Hamilton-Jacobi equation, this was the definition of P, then this state feedback control law, which I described, solves this problem, is the solution to this optimal control problem, the infinite horizon problem where, you know, my costs were Bregman divergence. This is the claim. And as I said, the way we use this theorem is, depending on the application, you have freedom to choose either Q or R. I'll give you many examples. If you choose Q, then you should find all R's and M's that satisfy this equation, which was 0.2, I guess, on the previous slide. And then M is really, we don't really, it's not as meaningful. The meaningful object is R, the cost on the control, if you've chosen Q. You tune M until you find an R that's acceptable, and then you write down your control law. If you choose R, you do the same thing to find an acceptable Q. I'll show you examples of this very soon. I just want to make a comment about what happens when, so what I looked at was the full information case. In many cases, what's more reasonable is I don't have access to the state. What I have access to is a noisy observation of the state. This is sometimes called measurement feedback. And so again, if you look at the vantage point of the controller in the measurement case, if I'm sitting at time I don't know the state anymore, but I can construct my best estimate of the state given the past observations. That's the conditional mean of the current state given everything I've observed till the current time. And this is very easy to find from the Kalman filter. And what this state estimate is kind of independent of, well, not the state estimate. The error is independent of the control that I do, but anyway. So I can take the state and I can write it as what I know and what I don't know, which is the randomness. This x tilde is zero mean. If everything is Gaussian, it's Gaussian. Its covariance is known from the Kalman filter, all of that. And so the optimal control problem that I will solve is now this. So in my Bregman divergence term, I put all the deterministic stuff to the left. I put all the random stuff to the right. So I'm looking at the Bregman divergence. You know, so when I take the difference of these two things, it is the state xi plus 1. But I've taken the state xi plus 1, I've broken it up into its deterministic and random parts, and I put the random parts on the right. And again, I've done this just so I can do the expectation. And so if you agree with this premise, or agree to do this, then the solution is exactly what I described to you earlier. The equations for P, Q, R are all the same. The only difference is your control now is a function of x hat, same function of x hat. And so this is called certainty equivalence. It holds in the quadratic case, which says that if you don't know the state, the controller can kind of ignore the estimation part and just plug in the best estimate of the state into its controller. And the estimator can ignore the control. It can just run its Kalman filter, whatever. Okay, so that's all I want to say. So measurement feedback is the same, again, provided you push all the randomness to the right, all the determinism to the left. I think I'm singing a Beyonce song or something about the left, right. Anyway. Okay, let me just do some examples and then wind up. So in these examples, because I don't want to get into Riccati equations, whatever, I'm going to do everything for a simple scalar system because I just want to demonstrate what we get. Okay, so the system will be, because I can do everything closed form here. It'll be a scalar system, this scalar system. Okay, so the first one is I'm going to put an elastic net on the state. So the absolute value of x plus a little bit of a quadratic term. And I'm adding this a little bit because if I don't add it, I don't have strict convexity. And so sometimes that bothers me. And so this is customary to do. This will still induce sparsity, as you will see in a moment. And so if you run through the machinery that I just described, if you want things to work, if you choose an m, for any m that you choose, m is now a scalar, this is the cost on the control. Okay? Now, if you look at this thing, you know, I want this cost to be convex, and so I need the coefficient of u squared here to be positive, and so that puts a constraint on what m's I can choose. So I cannot choose m willy-nilly. There's some range of m's. You know, so if A is unstable, any m works, but if A is stable, I have to make sure that the m I choose guarantees that this is positive. But that's what I was saying. So you can look at this. If you look, for example, at the leading order terms, you know, there's m's here, but there's an extra m in the numerator of both of these. So the bigger m is, the more penalty, if you will, on the control. But typically this cost on the control, it's piecewise quadratic, if you will. But again, you can choose m to your desire. Now, more interesting is what the optimal control is. Again, the way you find the optimal control is you find the Fenchel dual of this, and you take the gradient of the Fenchel dual. You get a piecewise linear control, which is this. Okay, so this is explicitly what the controller is. Let me show you its performance. So again, as I said, you know, so I'm taking, these are, so it's an unstable system. In the epsilon net, I took epsilon very small. I took a small m. So this is the cost on the state. It's an elastic net, so it almost looks like, you know, an absolute value function. There's a tiny bit of quadratic on top of it, which you can't see. For small m, we're not putting a lot of penalty on the controller, so it's quadratic, but very barely. And so if you look at the performance again, so here I'm looking at the absolute value of the state. The red is the LQR. The blue, you know, because I'm not being very demanding of the controller is not penalized a lot. It takes the state to 0 after one step, and then after that it deals with the noise. Okay, so it's very different behavior from the LQR. You might say, well, I should penalize, you know, maybe the state more. And so if you up this m, you get something that's more quadratic. Maybe this you like more. And so again, here, this is not as aggressively pushing me down to 0. But, you know, it's still doing a better job of that than the LQR. Okay, so you have some flexibility in terms of what you want through this parameter m. But the cost on the state is kind of quadratic looking. It's a piecewise quadratic. Let me do another example. We can take like a peak constraint control. So this is what we saw earlier. If I'm below a threshold t, I just quadratically penalize. If I'm above t, I'm disallowing it. Okay? So you can go through the machinery. Again, you know, so you choose an m, you do Fenchel duals, all this business. You find the q. This is what you get. Again, it's piecewise quadratic. If you look at this one now, you know, to get a convex q, this coefficient has to be positive, which means that a has to be less than 1, has to be stable. And this is totally expected because you cannot hope to stabilize an arbitrary unstable plant if you're peak constrained. You know, because if your initial state is too big, it'll run away too fast. The peak constrained guy cannot catch up. And so that's very natural that this was the answer. That's what I just said. The controller, again, is piecewise. It's actually interesting. It's linear up to a point, and after that point, it just levels off at t, as you would expect. Let me show you the performance. So again, here is the cost on the controller. It's infinite once, I guess I took t equal to 4 here. And, you know, for this value of m, we thought this was a reasonable cost on the state. And you can kind of see the performance. So here I'm showing you the absolute value of the state. So here, because we are peak constrained, the LQR isn't. We do a little bit worse than the LQR, but not a whole lot, because we're peak constrained. But here you see this is the actual control signal. We're constrained by 4. So this guy has put in a lot less effort to get this performance than the LQR. Okay, so this is the effect. So we've put in a peak constraint. You know, you might care about safety control. So now I'm going to put a limit on the deviation of x from 0. So you might have a robot and you want it to go, you know, up the stair and not bang onto the sides. So this is supposed to be that scenario. I'm giving infinite penalty if you exceed t. Okay, so I'll show you some of the steps here. So if this is q, p was m plus this thing, so it's this object. P star, you take the Fenchel dual, it's this object. R star, you go, you know, P star plus R star was a quadratic, so you can find R star, it's this object, who cares? And then, you know, if I take the gradient of this thing, well, that's the R, if you want to know what the R is. But you can get the optimal controller. So this is the controller. Again, it's piecewise linear. I would not have guessed this without this machinery. Let me show you the behavior. So the red is the cost on the state. So my safety guardrails are minus 0.1 to 0.1. I don't want the state to exceed this. For this value of m, this blue curve is the cost on the control, which looks reasonable to me. Again, it's piecewise quadratic. And so this is the behavior. So these are the I don't know why he used green. It should be red, I think, for safety. But anyway. These are the margins. This is where the safety controller that I just showed you, this piecewise controller behaves. And the other one is the LQR. I mean, it doesn't have the safety built into it, so it exceeds these bounds quite often. Okay? So we can actually build in, you know, a constraint like this and construct a controller. And again, these are non-obvious. I mean, this is what it is. Okay? Now, everything I showed you was, you know, piecewise linear. Doesn't have to be. You can get more exotic than that. So I just randomly chose this as my, so I'm putting exponential cost on u. I don't know why you'd want to, but let's assume you do. And if you push through this machinery, this is the u that you'll get. So it turns out the u, the optimal control, is kind of logarithmic in the state. Because this guy doesn't really want to expend anything on the control. So its growth with the state is only logarithmic. And for this reason, it turns out that if you insist on this kind of penalty on the control, your controller will only work with a stable A. You're penalizing, you're tying the hands of the controller so much that it can't really deal with an unstable. But you can get like some crazy logarithmic controller, and you can look at its behavior. Again, it's not as good as the LQR because you've really constrained what it can do. But again, if you look at the control signal compared to what the LQR does, you know, it's putting in a lot less effort. And so maybe that matters to you. You can do quantization. You know, if say your control only was allowed to do 3 things, up, down, or 0, how do I design an optimal controller if this is all the controller can do? Right? There might be very simple controllers where this is all you can do. Well, this control you can think of, if it's in this framework, it'll be the gradient of the Fenchel dual of the cost on the control. And so from this, you can go back and actually figure out what the Fenchel dual is by just integrating this out. It's something. And from here, I haven't done it because I was too tired last night. You can, you know, find R and Q and M. And so I just want to convince you there's a lot that you can do with this. So even though we insisted on Bregman divergence, and I moved the random stuff to the right, and then I had to insist that the cost to go is quadratic, there's still a lot of flexibility. So to conclude, Non-quadratic convex costs are rarely used in stochastic control because, as I said, computing this expected cost to go is often, to put it mildly, intractable. And so the idea here was to introduce Bregman divergence. Again, if you want to remember anything from this talk, is that the closest thing to quadratics is Bregman divergence. It allowed us to compute the cost to go. Again, the trick was you put everything deterministic to the left, everything random to the right. We had to insist that the cost to go is quadratic so that it would be a Bregman divergence itself. The optimal controllers are nonlinear state feedback laws. Stability comes for free. Certainty equivalence holds. If you don't observe the state and you have estimates of it, you just plug in the estimates into your control law. There's total freedom in choosing either the cost on the state or the cost on the controller, as I showed you. But once you choose one, the other one is, you have some flexibility with it, but you cannot choose it. I cannot say I want an L1 cost on the state and an infinity cost on the control. That I cannot do. I can choose one, and then the other one I can play around with the M parameter until I like what I see. But nonetheless, it gives us a lot more flexibility in the designer of the controller than the standard LQR, LQG, which just gives you linear controllers. And I guess I did some examples for you. So I hope I didn't rush it too much. I will stop here. Thank you.